nanoHUB.org.
Online simulation, and more for nanotechnology.
We talked about the electromagnetic spectrum, but we didn't define exactly what do we mean by the electromagnetic, or the EM for short, spectrum or optics. In fact, the term EM or electromagnetic denotes the electromagnetic wave, the physical nature of the classical light wave or the electromagnetic spectrum. So, in fact, the electromagnetic wave is like combined of electric field and magnetic field interrelated together in a special relation or a set of special equations that are called Maxwell's equations. So they are governed by Maxwell's equations, and Maxwell's equations are just a collection of physical phenomena that has been observed before the time of Maxwell that describe the electric current that is originating due to time-varying magnetic fields, and magnetic fields originating due to time-varying electric fields, and so on, like the Ampere law and the Gauss law, and so on. So the idea is that the propagating electromagnetic wave is a function of space and time. It's a harmonic function. Let's imagine it as a harmonic function that is propagating over time towards the propagation direction. And it maintains a special relation between the electric field vector here and the magnetic field vector here. So that if we take a plane here, that taking the components of the electric field and the magnetic field, taking a plane perpendicular to the propagation direction, we can imagine that if this is the propagation direction, the electric field vector will be here, and the magnetic field vector will be perpendicular to the electric field, perpendicular to the propagation direction. And one of the specific characteristics of the electromagnetic wave is the wavelength that defines the distance between similar points on the harmonic function of the electric field or the magnetic field in space. So if you take at a specific time point, you measured the distance. And you took a shot. Imagine that you took a shot of the propagating electromagnetic wave, and you measured the distance in that picture between two crests or two dips, or two same points on the electromagnetic wave. The distance is called the wavelength. In fact, understanding the physics of the electromagnetic wave and taking Maxwell's equations in analyzing different problems helped us over the time to understand how the light interacts with different surfaces and different materials. So what you see is actually what reflects to your eye due to light hitting different surfaces or interfaces. So for example, when light hits a material, any material can be transparent or opaque, the light reflects some of the light power reflects to your eye, and some of it refracts or bends inside the material or transmits inside the material. So the phenomena of reflection and refraction is well explained by Maxwell's equation and the boundary conditions that solves Maxwell's equations at different interfaces between different materials that give rise to the reflection and refraction phenomena. And if we get one step forward, you will see that if some of the light goes through the transparent material, and if it is made of a thin film, again, some of the transmitted power can reflect back and hit the interface between the air and the material, and some of the power will transmit to your eye, interfering with the original reflected component. And when the light goes this distance, it accumulates phase, and it can give rise to constructive and destructive interference, where the two reflected components, the resultant of the reflected components from the original component and those that has been transmitted and reflected back and forth all the way till it reaches your eye, gives rise to constructive and destructive interference. That the two components will add up to either add up to give rise to constructive, empowering the power reflecting to your eyes, or destructive or canceling the effect of each other so that your eye wouldn't see any reflected rays or any reflected power or any reflected light back to your eye. In fact, this has very useful applications in developing, for example, anti-reflection coatings for glasses, anti-glare coatings, and many other applications. And one beautiful thing that we see every day, that for a bubble, like blowing bubbles, playing with bubbles with kids, you will, if you look at the bubble, you will see different beautiful colors at different points on the surface. And actually, that is because of this phenomenon, constructive and destructive interference, because the thickness of the film is not the same over the surface of the bubble. Thus, you see these beautiful colors reflected to your eyes. Other phenomena that have been observed is called the diffraction, which is due to the interaction of light with periodic surfaces that has periodicity close to the wavelength of the incident wave. So this periodic structure or a grating structure will cause some of the incident wave to diffract in different directions according to the conservation of momentum between the momentum of the incident wave and the momentum added by the surface grating. So it can cause a scattering in specific directions, maybe here, maybe there, and there. And this phenomena also can be described using Maxwell's equations as we discussed before.